Hello and welcome. Today we are diving into one of the coolest and most elegant algorithms out there in machine learning, the support vector machine, or SVM. If you've ever wondered how a machine learns to find the absolute best way to separate different groups of things, well, you are in exactly the right place. So here's how we're going to tackle this. We'll start with a really simple idea I like to call the widest street. From there, we'll meet the most important players in this whole game, the support vectors. Then we'll see how SVMs handle messy, real-world data. And finally, we'll uncover its secret weapon, the amazing kernel trick. By the end, you'll totally get why this thing is so powerful. All right, let's jump right in. The entire logic of an SVM really boils down to one simple, intuitive goal: finding the best possible line to divide our data. To make this super clear, just picture a field. You've got a bunch of apples on one side and a bunch of oranges on the other. Your job is to build a road that separates them. Sounds pretty straightforward, right? But what actually makes one road better than another? I mean, you could draw all sorts of lines that get the job done. But take a look at the road on the left. It's kind of hugging those data points pretty closely. There's not a lot of breathing room. In SVM, it's not interested in just any road. It is on a mission to find the best road, the one that stays as far away as possible from the closest apple and the closest orange. It wants to build the widest, safest path imaginable. And you know what? We actually give this widest street a technical name. We call it the margin. The entire singular goal of the SVM algorithm is to find a dividing line that makes this margin as wide as it can possibly be. This whole focus on creating the biggest buffer zone is exactly why it's known as a maximal margin classifier. And that line running right down the middle of our super wide street, that's our hyperplane. That's the final decision boundary. Now, if our data just has two features, like, say, height and weight, the hyperplane is just a simple line. If we add a third feature, maybe age, it becomes a flat plane. And if we have tons of features, which happens all the time in machine learning, it's called a hyperplane. It's the exact same idea, just in dimensions that are a little tricky for us to picture in our heads. Okay, so we've got our street, we've got our center line, but what actually dictates where the edges of that street are? This is where the algorithm gets really, really smart. Just think about it for a second. To figure out how wide you can make that road, you don't need to look at every single apple and every single orange. Nope. You only need to pay attention to the ones right on the frontier, the ones closest to the other side. They're the ones that dictate just how wide our margin can get. And these incredibly important data points, they get a special name. They're called support vectors. They're the points sitting right on the edge of the margin, the ones that are the toughest to classify. And they are literally supporting the entire hyperplane. If you were to move one of them, the whole street would have to shift. This is what is so incredibly elegant about SVMs. See, most other machine learning models have to look at every single data point to make up their mind, but not an SVM. You could take all the other points, the ones far away from the boundary, and move them all over the place, and guess what? The hyperplane wouldn't budge. Only the support vectors matter. It's a ridiculously efficient way to model the data. So far, we've been living in this perfectly neat world where our apples and oranges are easy to separate. But let's be real. Real-world data is almost never that clean. It's messy. So what happens then? Imagine there's one apple that somehow ended up way over in orange territory. It's an outlier. Now, if our algorithm is a total perfectionist and tries to separate everything perfectly, that one single point is going to force it to create a really weird, narrow, and flimsy boundary. It might be perfect on paper for the data we have, but it's probably going to be terrible at classifying new data it's never seen before. And this brings us to a classic trade-off, the hard margin versus the soft margin. A hard margin demands absolute perfection, which makes it brittle. A soft margin is way more practical. It says, you know what, it's okay to make a few mistakes. I'll let a few points be on the wrong side of the street if it means I can create a much wider, more robust boundary overall. And for pretty much any real-world problem, this is the way to go. So how do we control that flexibility? Well, we have a little tuning knob, and it's usually called C. You can think of C as the cost or the penalty for making a mistake. If you set a high C value, the penalty is huge, so the model tries desperately not to misclassify anything, even if it means creating a narrow margin. But if you set a low C value, it's more forgiving. It allows for a wider, more general street, even if a few points end up on the wrong side.
Okay, so we can handle outliers. But what about data that isn't just messy, but is fundamentally impossible to separate with a straight line? This is where we get to see the SVM's true superpower. I want you to imagine your data looks like a donut. You have one class of points that forms a ring around another class of points in the middle. Try as you might, there is no way you can draw a single straight line to separate them. So, is the SVM useless here? Absolutely not.
The solution is just genius. If you can't solve the problem on a flat 2D sheet of paper, what do? You add a dimension. Imagine taking that donut and sort of popping the center points up into a third dimension. All of a sudden, from this new vantage point, you can just slide a flat sheet of paper, our hyperplane, right between the two groups. It becomes easy. And that simple plane in 3D, when you look at its shadow back down in our original 2D world, forms a perfect circular boundary.
And this is what we call the kernel trick. Now, here's the thing. Actually transforming huge data sets into higher dimensions would be a computational nightmare. It would take forever. The kernel trick is a beautiful piece of math that lets the SVM do the calculations as if it were in that higher dimension without ever actually doing the heavy lifting of the transformation. It gets all of the power without any of the crippling cost. It's amazing. And there are different kernels or functions we can use to do this. The linear kernel is just our basic straight-line SVM. A polynomial kernel can create nice curved boundaries. And the radial basis function, or RBF kernel, is super popular because it's fantastic at creating those complex, circular-type boundaries, perfect for our donut problem.
Okay, so let's tie all this together. Let's do a quick recap of what makes the support vector machine such a cornerstone tool in the world of artificial intelligence. Under the hood, this is all a big optimization problem. But you can think of it like this. The math is trying to make the margin as wide as possible. And it turns out making the margin wider is the same thing as making another mathematical value smaller. So the computer's job is just to find the setting that makes that value as small as possible, while still keeping all the points on the correct side of the street. And this whole approach leads to some major wins for SVMs. First, they work incredibly well even when your data has tons and tons of features. We're talking high-dimensional spaces. Second, they are super memory efficient because remember, after all the training is done, it only needs to remember the support vectors. And third, they're so versatile. Thanks to the kernel trick, you can use them for simple linear problems or incredibly complex ones. I think this quote just nails the difference perfectly. Other algorithms might be happy finding just any line that gets the job done. An SVM is different. It's an optimizer. It is laser-focused on finding that single best possible line by making that safety margin as wide as it can be. It gives you the highest confidence in its decisions.
So I'll leave you with this final thought. This core idea of not just finding a solution, but finding the optimal one with the most room for error. That's an incredibly powerful concept. Think about it. In a world filled with messy data and uncertainty, from diagnosing diseases to making financial predictions, where else could finding the best possible boundary change everything?